When we're studying maths, we're often talking about transformations, and when we're studying functions, there's different sorts of functions and a lot of transformations that we study. A lot of them carry over, so this would be the beginning of an important area of study in its own right. But at the moment we're only going to look at transformations of quadratic functions, and transformations are a mixture of two things. They're translations and what's often called dilations. Now that's about, if you remember your basic geometry from your earlier grades, translations slide things, so that's about position and movement. Movement in a plane. And the other one, dilation, is a shape change, so it's like stretching. Or compression. And it's the important thing, it's a shape. It's about the shape, the change in the shape. So when we're looking at quadratics, our basic function is y equals x squared. We're going to look at a, b, c and d as parameters or constants, and they're real numbers. They can be any real number. So a, b, c, d are constants or parameters. So again, this is very important, not just for quadratics, but later on when you do other things like trigonometric, exponential, logarithmic, and other types of polynomials. There's many different sorts of things where we look at transformations. So very important. So these things together comprise of the transformations we're going to consider. Okay? So translations and dilations. Don't get the word transformation and translation mixed up. Okay? So translations are transformations, but not all transformations are translations. Some of them are also dilations. Some of them are dilations, I should say. Okay, so A, B, C and D are just numbers, real numbers. Now you might remember our friend y equals a outside of x minus h, all squared plus k. That is a surprisingly helpful form of the parabola, because if I was to write this, you can see some similarities. We've got a outside of b, outside of x minus c, and then close the brackets twice. That's all squared, and the d. What's the difference between the a and the b? I'll show this graphically soon, but a is outside, so the a is not actually squared. Everything inside squared. The b does have the squared effect because it's inside. Alright, so it's inside. So let's look at what all these things do. Make sure you copy your notes as well as we go. So basically we can see I've got plotted y equals x squared here, and from what we know, it's our standard parabola. So if we start transforming that, we put in a, b, c and d. Now that is not a mistake, that is a minus sign there, because it's helpful. Perhaps you can reflect on the turning point form, why that is helpful. So we've got a, b, c and d, and we're going to have a bit of a play around and see what each of them do. So what we'll do is switch off our pen and have a bit of a play around. So what we've got, if I put in, I've got at the moment these set to different values, these slider bars, so I'm going to set them to a fairly neutral position. I'm going to make C and D 0. Now C and D, spoiler alert, basically they change the position, and A and B change the shape. So A and B are actually linked to dilation, and C and D are linked to translation. Now if I switch on the other function, the only difference will be this. So I'll switch that on now. What does it do? Okay, as I said, it changes the shape. So, but in what way does it change the shape? Well, if we look at when it's 1, it's the same as the standard parabola. So I'll click it over there. Alright, it's on top of the blue one. Okay, and if I make it bigger than 1, it gets pointier and narrower. So that's called a vertical stretch when that happens. So we'll write that in. We've got so when A, whoops, I haven't got the pen on. I've got geometry thing on. A is greater than 1. We have a vertical stretch. By a factor of A. Whoops, factor. It's a T. So if A equals 2, it's got a vertical stretch by a multiple of 2. Factor meaning multiplicative effect. Okay, so if A is less than 1, let's see what happens. So A is now less than 1. Alright, whoa, what happened there? Look, it's horizontal when A is 0. Oh, look, uh-oh, we've broken it. We've broken maths. We've broken a parabola. No, in fact we haven't. What we do, we need to write the next relationship here. We haven't broken anything. So when A is less than 1, but A is also got to be greater than 0, because we saw what happened. It went horizontal. Now what that means is that it knocks out the whole squared term and you've only got a constant term. So that's why it goes flat. It turns into a constant function. But the range we're talking about, if A is in that range between 0 and 1 exclusive, we have a vertical compression. So it's a dilation as well, vertical compression by a factor of A. It's a dilation and a shape change. It's whatever the value of A is. So let's look at some examples. We've got 0.5, so it's got a vertical compression by a factor of 0.5. This one here, 3, it's got a vertical stretch or dilation by a factor of 3. Okay, or that one would be a dilation by a factor of 0.5. Okay, it's a compression, that's a stretch. Okay, so I'm just going to return that now back to 1, so we have our neutral one. What's the difference between A and B? Well, like I said before, B is squared, so how do we tell them apart? Because see, this changes our stretch and compression too. Do they do the same thing? Well, you wouldn't think so if one's squared and one's not. So I'm going to make that disappear, and we're going to go down to a couple that I prepared earlier, and basically you can see what I've got here, this one and this one. Now one of them I've got A equal to 3, that's in this last one here, and the other one I've got B equal to 3, and so when B is 3, A is 1, and when A is 3, B is 1, just to see what their effect is. Okay, and so they aren't the same, so I'm going to get rid of our base parabola as well too. They aren't the same, so when the effect of A is this, I suppose I should have the original parabola on just to see. So the original one's blue, this new one here is purple, and I hope you're not watching on a black and white. Haha, that's a old-fashioned joke, sorry. So basically look at that, it is quite a difference, isn't it? So the fact is it's a squared effect, so the green one makes a bigger difference. So it this is a case, there's a difference here of these. So when we're looking at A is there's the geometry tool again, I don't want that. A is what's called A times f of x. It's a transformation. So whatever the function is, it's A times the function. Now get used to this, because you'll see this with other things like, you know, like all those functions I mentioned before, the ones you're going to see in the future. This one is the function f of bx. So see how the b is involved in the function, and that was the squaring part before. By the way, we're going to be doing c, and c is f of x minus c. Some people use a plus there, I'm going to use a minus. And d is f of x plus d. So get a copy of those. A times f of x, f of bx, f of x minus c, and f of x plus d. Now, back to what we were doing. So if I just take, you probably appreciate that a equals 1 and b equals 1 match the function given, x, the base function x squared, so I'm going to return them back to that so I can see the effect of c. Now, what's going to happen if I better switch the function on? Okay, so what I've done is take c from 0, where it fits over the original parabola, and if it's minus a number, so it's at the moment it's minus x minus 2, x minus 3, it's moving to the right. So what we would have there is pen, right, that would be y equals x minus 3 all squared. That's what that would be. What would y equals x plus 3 look like? X plus 3 all squared. Well, for that to happen, we have to get a plus in there, we have to minus a negative. So we would have to have the c set to negative 3. So that would be a case of c equals negative 3, and that would be the case of c equals 3. Alright, well, let's have a look at that. Turn the pen off and let's look at that. So there we go. So it's negative 3 now, and you can see what's happened. So it's moved to the left. So with x minus c, in the case of x minus c, if we have c is greater than 0, so it's a positive, it moves, it translates to the right. By c units. Okay, so it's a number of units. All the points move to the right if it's positive, and like this green parabola here, if c is negative, it translates to the left. Translates to the left by c units. So that's every point, including the turning point. Now that's why it links to the turning point formula, because what it's doing, see the turning point is one of the points that moves, so that's why it links to the turning point form, x minus h. Alright, remember the x minus h inside and the y minus k. Alright, so the h is the same as the c, it's just an arbitrary letter. Okay, returning c back to 0, d translates every point on the parabola up, and that's a bit like, it links to the plus k with our turning point form, doesn't it? Okay, because the turning point is one of the points that go up. So it's d, if d is greater than 0, it translates the function or the curve, the parabola, d, whatever d is, its number, units up. And if d is negative, it's d units down. So in conclusion, hopefully you know what a transformation can be. It can be a dilation, or it can be a translation, i.e. a shape change or a position change. And of course these link to the turning point form of the parabola, because the turning point is one of the points that moves, that translates. And basically what we have done here is use the turning point form, and we've put in an extra transformation, and that one is a bit rare anyway. B is rare, so it's really just the turning point form of the parabola, and we're using that for transformations, which will come in very handy with curve sketching and things we'll do later. The only thing that hasn't been mentioned is that of course you can combine all of these together, which we'll do soon, and you don't just have one in operation necessarily. It can be a few. Okay, so you can have them all going and really blow your mind, see? And that, woo! Alright, about time I stop this video.